Sir, can you please tell some sources to refer for the course, like more other than lectures?
There is one NPTEL course that you can refer. So actually there are two courses on digital signal processing. I'll just put the link in the chat box. So this is
Okay,
one
sir.
of the courses that is, I think this is a good resource if you want to refer to lectures. Otherwise, the textbooks I think you already know. But if you are interested in video lectures, then this the course that I have. So the message that I've just sent, that one is I think quite good.
Thank you, sir.
Okay, so let me just share my screen. Okay, so is it visible to you all?
Yes, sir.
Okay, so let's start. So basically, in this tutorial, we will look at some questions, some MATLAB based questions on interpolation and decimation. So basically, the sampling rate conversion. So there are these three questions that we will take a look at. So let's start. And the first one says that we are given some sequence x of n is cos 0.125 pi n. We have to generate the samples of the signal and we have to decimate it using some values of d. D is given to 4 and 8 and we have to plot the result. So just let us quickly recall what this decimation or what this downsampling meant. We said that we have an arrangement something like this. This block is known as a downsampler. We pass a sequence x of n which has a rate of rate sampling rate f of x, and when it passes through this block, the output sequence is has a different rate, and the rate is fx by d. So we have decreased the sampling rate by a factor of d. And generally, when we do this, this overall operation of downsampling, what we say is that before this decimeter, there is also one another block uh, which is a low pass filter, or rather a band pass filter, and its job is to ensure that the signal before passing through this decimeter, it gets band limited so that we can prevent any aliasing that may occur. So if we look at the frequency domain, it was like this, that if this was the spectrum of the original signal sequence. So if let's say this was the spectrum, and you can see that this sequence is uh, band limited, or the spectrum of the sequence is band limited between minus pi by 3 to pi by 3. So this is an example. And here, if I have d equal to 3 and I pass it this sequence through this block, then what will happen is that this frequency axis will get scaled by a factor of 3, and this will go from minus pi to pi. Another thing that happens is that the magnitude decreases by a factor of d, and you will see that this uh, the sequence will repeat after that, right? So most important thing is that it is from minus pi to pi. So you can see that if this was not from minus pi by 3 to pi by 3, but let's say it was from minus pi by 2 to pi by 2, then in that case what would have happened is that when I if let's say d was still 3, then it would have become minus 3 pi by 2 to 3 pi by 2, and in that case it would have exceeded the pi value, and therefore there would have been some aliasing with the uh, other peaks, right? The remaining frequency spectrum. So that is the point, and that's why we have a block of bandpass filter before this block. Now let's quickly try to. This was just to remind you what this decimation operation was. Now let's quickly uh, do this on MATLAB. So I'll open a script. Let me just call it session 3. This is the third MATLAB session. Okay, so first of all, we have to plot the signal, and we need decimation of 2, 4, and 8. So what I'll do is I'll define the uh, time index or the values of time. So it's good to take something that is divisible by 2, 4, and 8. So I'll take 32. And I define the sequence, which is cos 0.125 into 5 into n. Right? This was the sequence. Uh, so we have to plot for 2, 4, and 8. I'll just use subplot so that we can plot it in the same curve. So let me make it 4 cross 1, and I'll select the first one. So in this case I can directly say stem, the time index, which is n, and now the sequence, which is x. Now I don't yeah, so let me just plot this. I hope it works. Yeah, so this is the sequence, simple as that, and you can see that it is a cosine function, right? So this is basically how we have obtained some samples of uh, this sequence. Okay, now let me take the case when d is equal to 2. When this sequence is passed through, d is equal to 2 downsampler block. What happens to the sequence? I will make a new sequence y, and I'll use this function decimate, which is a MATLAB inbuilt function, and I will take this original signal that we had, and I will decimate it with the value of d, which is 2. And let me plot it in the same grid of plots. So I'll use subplot 4, 1, and I will select the second plot of this one. So here I'll plot using stem because it's a discrete sequence. So we use stem here. Now, one thing to notice: what happens to n and what happens to y. So first of all, we cannot have n from 0 to 32 now, because here then there were 32 sequences, because x, so there was n going from 0 to 32, which means that there were 33 time indexes, and x was being evaluated at each of them. Now what happens is that n will change because we have decimated the signal. So if d is 2, what happens is that x, let's say x starts from x0. So x0, x2, x4, and so on, the signals will be obtained in y. So we will also have to decrease the number of time indices. So I'll just take the time indices as 0 to 16. So I have taken half of them because d is 2, and the number of sequences will be half. So number of the number of the number of values of, or the number of samples will be halved. Similarly, I can uh, take y consistent with this time index. So I'll say 1 to 17, right? Because the index of y will start from 1. So I have taken it from 1 to 17. And the time index is starting from 0. So I have taken up to 16. In both the cases, they are a total of 17, right? Similarly, let's quickly do it for, I'll just copy this part to do it for b is equal to 4. uh, I just have to, I'll plot it in the third plot, I will take this again the half. So I'll just divide 32 by 4, and so this is how it will be. And finally, let me plot for d is equal to 8. So in this case, I'll select the fourth one, fourth subplot. I will make this go from 0 to 4, and this will go from 1 to 5, right? And let me just plot it now. So if I run this, these are the plots. So this is the original sequence. You see that when I decimate by d is equal to 2, this one is what I'll get, right? Then I decimate it with d is equal to 4, I get this. So and finally, so you can see that let's say if I look at this one, for d is equal to 2, I have this value, and I have this value. So this one goes to 0, and similarly, so basically every other value will be selected out of the original sequence. For d is equal to 4, again every second other value will be selected, and similarly for d is equal to 8. So you see that when we have d is equal to 8, this signal is not recognizable. Even for d is equal to 4, we can still see that it's first increasing and decreasing and so on. So you can still make sense that this is a cosine function. But for d is equal to 8, that is not the case. And that is because for d is equal to 8, there has been aliasing. So if you look at the frequency domain, you will see that there will be aliasing, because now the frequency spectrum is not between minus pi to pi. And that is why in the last case, when we have used d is equal to 8, the signal cannot be recognized. We cannot say that this is a cosine function. So that is how it is. So that's why it is important that we first of all pass the signal through uh, uh, a band pass filter appropriate uh, uh, of the appropriate frequency range before we decimate it. Sorry, before we downsample it. Yeah, so that was part one, question number one. Are there any doubts in this one? Any doubts?
No, sir.
Okay. Okay, so let's move to question number two. Now in question number two, we have this sequence xn is equal to cos pi n. We have to again generate the samples, and we have to interpolate them using I is equal to 2, 4 and 8, and then plot the results of interpolation. Now just like decimation, we can also, so in decimation we were trying to reduce the sampling rate, and in interpolation we are trying to increase it by a factor of I. And so let's quickly look at what it was. So again we have this block of upsampling block. We pass the sequence which has some sampling rate f of x, and the output sequence will have the sampling rate of I times f of x. This was the main idea of this upsampling. And to obtain the overall interpolation, what we do is that this block follows one another block of a low pass filter. And so basically what, as a result of passing through it, what will happen is that all those values that we have selected, so for example if xn was x naught, x1, x2 and so on, what will happen is that between x naught and x1 there will be I minus 1 number of uh, uh, more sequences inserted, and then we can interpolate them when we pass them through this low pass filter block. That was the idea. And if we look at the in the frequency domain, this is the DTFT of the input signal, and it's between minus pi to pi. When I pass it through interpolator, what happens is that this frequency gets scaled by a factor of I, and so it goes from minus pi by I to pi by I. Now, when I will use a low pass filter, I want it to have a band limit of minus pi by I to pi by I, so that I can uh, take this part out of of the output. And that's the main idea behind this overall interpolation, right? So here the frequency axis gets scaled by a factor of 1 by I. And so let's look at question number 2, where this is done. We have xn is equal to cos pi n, and I has to be I equal to 2, 4, and 8. And the good thing about interpolation is that there will not be any aliasing here, because we are not increasing the frequency range, but we are decreasing it. Okay, so let's do this. Let's do the part 2, question number 2. So again, let me take some n. Well, let's just take n is equal to 0 to 30. X is cos pi n. This was the signal. I will, so we have to plot for I is equal to 2, 4, and 8. Okay, so I'll just plot for I is equal to 2 and 8. So let me take a subplot where, so it's a grid of 3 cross 1 plots, and I'll select the first one. And first of all, I'm just plotting the original sequence. So the time index and x goes from 1 to 31, right? Because there are 30 number of samples, 30 number of time indices. So let me just do this. Let me just run this, and I have got this sequence. Okay, so you can see that it's a cos, the cos function. Now let me take I equals to 2. Now to interpolate, I will use the function interp. So, and it will give me some other sequence y. So I'll give as the input the original sequence x and a factor of I, which is the upsampling factor, and I will subplot uh, by in the second plot, right? And again, in this case also, I will have to change for this y. I'll have to change n and x. So n will double because I have taken I is equal to 2. So the number of time indices will also double. So instead of, because n was from 0 to 30, now I will have from 0 to 60. And this will be y, right? It will also have 60 number of samples. And similarly, let me also plot I for I is equal to 8. I am not plotting for I is equal to 4, but that's also in the same manner. And then this will become 240, right? Okay, let me just call the signal some Z to avoid any confusion. And I'm going to plot this now. Okay. So this is what I've got. So you can see that this was the original sequence cos pi n. First of all, I have upsampled it by a value of 2. So when I upsampled it by a value of 2, in one period, the number of, so here in one period we had 2 sequences. Here in one period I'll have 4 sequences. So it has doubled. And similarly here, I will have 16 sequences. So in that way, the number of sequences per period has increased because of the upsampling operation. And yeah, so these are the three plots. Okay, and this is the end of question number 2. Finally, let's look at question number 3. In question number 3, we have this sequence x of n is equal to cos 0.125 pi n, same as the question number 1. And we have to change the sampling rate by a factor of 3 by 2 and 3 by 4. So now we have the sampling rate conversion by a rational factor of I by d. This is the so this is what this question addresses. So if you recall, when we have to change the sampling factor by some other rational factor and not just some integer value, then what we do is we do it by first of all having some upsampling followed by some downsampling. Generally, upsampling is followed by a filter, and downsampling is previous to downsampling we have a filter. So in this case, when we have to uh, com- uh, do the sampling rate conversion by a factor of I by d, we combine these two filters into a single ideal low pass filter. And this operation, what we get at the output is ym, which has the rate equal to the inputs rate multiplied by I by d. And so this I by d is what we have to select by selecting I and d respectively. So this is how we do the sampling rate conversion by some fraction. So let's do this also. Let's do question number 3, and let me just take, just like previous in the previous case, n is equal to 0 to 32. The sequence is x, which is cos 0.125 I n, right? And I will use subplot. First cases. So there are three cases that okay, there are two cases that we have to consider: 3 by 2 and 3 by 4. So first of all, let me plot the original sequence, which is quite straightforward. I'll just say n comma x. Okay. Now, one thing that we can first of all determine here is that what is the sampling frequency of this x. So I'll denote this variable original f of s, which is the original sampling rate of x. So that is basically omega naught by 2 pi, right? That's how we find out frequency. Omega naught is equal to 0.125 into pi. So I just take this and divide it by 2 pi. And this is the original sampling frequency. It will be equal to 0.125 by 2, 0.0625. And now let me take the first case, which is changing the sampling rate by a factor of 3 by 2. So that means that I is equal to 3 and d is equal to 2, right? Because that is what we saw. It is I by d. So I have defined I is equal to 3, d equals to 2. So I equals to 3 and d equals to 2. Now to resample, when I have to do both the things, so there is this MATLAB function called resample. It will take three arguments. The first one is the sequence, second one the value of interpolation, and the third one is the value of the decimation, right? and this is what y is. And we can similarly calculate what the desired f of s we will obtain after doing this operation of sampling rate conversion. So the desired sampling frequency will now become the original one multiplied with this factor of I by d, right? And once we have done that, we can find out n1, that is the number of samples of this new sequence that we have obtained after doing this uh, rational factor sampling rate conversion. So this new n1 will be start from 0, and it will have the number of elements. So the number of elements for uh, yeah, so here we had n, which had the same number of values as that of x. Here what we have done is we have obtained y, and y is obtained in a manner that its number of samples will be. So what we can do is we can see how many elements are there in y. So the number of elements in y can be found out using this num l. So but it will give me the number of elements in any array. Y is an array, so I will just use this. So if you look, if we evaluate this, so y has 47 elements. So when I run this, I'll get 47. So from 0 to 47, right? But we have also scaled it by a factor of, so now when we have to find out the number of samples, and also we will have to take -1 because we are starting from 0, and then we can, yeah, and then we can divide it by the this desired f of s, right? The number of the desired f of s, which is the frequency, the rate of the new signal, and that way we can get this n1. Okay, now I will plot this. So now the sequence, the value of n1, oh, I haven't, yeah, so now n1 has the same number of samples as that of y, right? And now we can plot it. Let me select the second plot, and I'll say stem n1 comma y, right? So just like we were doing in the previous case, we have uh, so in this case what happens is that we have I greater than d. So it means that there will be an overall interpolation, because because the factor was I by d and I is greater than d, so the overall sequence will be interpolated as compared to the sequence x. And similarly we can do for I equals to uh, I by d is equal to 3 by 4. So I is 3 and d is 4. Now in this case, d is greater than I. So there will be an overall downsampling. So let's say we this downsampled signal is z, which is, so again similar to just by using this resample function, I have defined this new sequence z. I will find out what will be the desired f of s, or what will be its sampling rate, and that will be the original sampling rate times I by d. And now we have to define the time index. So the time index will again be similar to the last case. We have the number of elements in z 0 to number of elements in Z minus 1, and we divide it with the desired f of s, and that will give us n2. And we can check to see if the number of elements are the same. So n2 has 23 elements, and z has 24 elements. Mm, yeah, I think there is some problem because it should not have 23 elements. Let me just try to plot this. I think it will throw an error. Yeah, because the lengths are not the same. Oh, actually the problem is that I started it with 1. It should have been from 0 because it's a time index. Yeah, now it will be fine. So now let me run it, run the whole thing, and this is it. So this was the original sequence, which was 0.125 cos 0.125 pi n. We first of all use the sampling by a factor of 3 by 2. So there is an overall interpolation. You can see that the number of samples per period has increased, and in this case, the third case, there is an overall decimation. So you see that the samples are more far apart, or the number of samples per period have decreased as compared to the original. So that's how it is. Yeah, so that was question number 3, and that's it. That was tutorial 8. Are there any doubts? Okay, so that was it. That was the tutorial on sampling. Sorry, on sampling rate conversion. Uh, and okay, if there are no doubts, then we can end this. Thank you.